two on the right side are the PLA materials from this video. What do you think what will be the deformation order inside this oven? Welcome back to my Tech Fun, to very interesting filament testing video. But first let's start with a question. What is the main reason for the popularity of PLA filaments? Actually, it is quite strong material, but the main reason is easy printability. And what is the biggest disadvantage? Well, it is brittle material compared to the ABS, compared to the PETG less brittle, but the main disadvantage is actually low temperature resistance. If you leave your 3D printed part inside the car on hot summer day, probably it will deform in first hour. And looks like the Polymaker solved this, and we have here HT-PLA in 4 different colors. And I have here HT-PLA-GF in 2 different colors, in black and white. And when I'm recording this intro, there is no information on the website, only I got a small PDF. Let me read a few specifications from that. HT-PLA, heat stable up to 150 degrees Celsius and print speed up to 300 millimeters per second. PLA printability, of course. HT-PLA-GF, reinforced with glass fibers, heat stable up to 150 degrees Celsius, heat resistant up to 110 degrees Celsius if it is annealed. Just to clear these two expressions, the heat stable, properly they mean here that without load they can withstand this temperature, and heat resistant, it is some kind of heat deflection temperature when we place some load on the test objects, and then we will follow when we start to deform. And actually my testing is somewhere between, because the ISO 75 standard uses bigger loads than mine, but I will do my regular testing methods, so these results are compatible with those which I did in earlier videos. But for PLA, basically this is 50-55 degrees Celsius if it is a regular PLA. About annealing, they only mention it for the glass fiber version and looks like quite aggressive, 30 minutes on 110 degrees Celsius. Usually I use the annealing 100 degrees Celsius for 1 hour, but of course this depends a lot from the size of the objects. My test objects are quite small, and even 30 minutes probably it will be enough. I only follow these instructions, but keep in mind if you have some bigger part, then that annealing must be a little bit longer. And why only for the GF? Well, I already tested this earlier. The regular PLA will deform during this annealing process. And these fibers, glass or carbon fibers, will help to keep that dimensional stability. And in this case, I will try to anneal both, but probably if I will see some deformations on the HT-PLA, I will not even do the testing, just want to present that shrinking and warping during this process. And maybe it is important to mention that not only this video, but the whole channel is sponsored by Polymaker, but this don't have any kind of effect to my measuring results and for the content of this video. In that PDF it is not mentioned, but properly on the website will. For the glass fiber versions, we need some kind of hardened steel or similar wear resistant nozzle. I have my regular testing methods, and those results are comparable with those which I did in earlier videos, and this can be found in that summary table for my Patreon supporters. But I will do that only with one color for each type, maybe white, because I tested recently too many black filaments. But with each color I want to print some basic test objects and to see is there any bigger difference between them, very similar like I did with that ESUN 12 different colors PLA testing video. So far only from one company I could see a PLA filaments with similar properties, and actually it's Filaticum, a Hungarian company. But their filaments are available only in Hungary or maybe in surrounding countries mostly, and the price of that filament is 3.5 times bigger compared to the regular PLA. So that's why I'm really excited about these filaments. Let's unbox these two filaments. Nice vacuum packaging, I can see desiccant inside. These bags are not resealable. It is so good to see the print settings on the spool too, because I don't have any kind of information in that PDF. And they are very similar, only the maximum printing speed on HT-PLA it is 300 and on the glass fiber version it is 350 millimeters per second. Anything else is same. Print temperature between 210 and 230 degrees Celsius and bed between 25 and 60. And if you need a drying, it is recommended to do it on 60 degrees Celsius for 6 hours. And B+ they include this information too. Spool weight is 140 grams. I'm not sure, but for the feeling I think these are those spools with the hardened edges, so they are AMS compatible, only I'm not sure if the glass fiber version is compatible too. Let's see how brittle are the filaments. This is regular PLA. I can completely bend it. Of course it's damaged, I will cut it here, but let's see the glass fiber version. It is more brittle, let's measure it. This tester you can download from printables if you want to check your filaments. I will try to use them in all cases when the filament is brittle. Okay, start deformation, approximately 30 degrees. Approximately 95, but I will check the footage. I think I will start a new column in that summary table for my Patreon supporters. Of course, this bending depends a lot from the moisture in it, but I will add the data always measured with the fresh spools. And one more time visually. HT-PLA will be printed on P1P and the glass fiber version on X1 carbon because it is equipped with a hardened steel nozzle, and in both cases I'm using the textured PI sheet. Settings in the slicer. From the regular PLA I just changed the temperature from 220 to 230 degrees Celsius. Everything else is unchanged compared to the default settings. The start looks good on both printers. This is P1P and this is X1 carbon. With open doors, of course. And the last vertically printed test objects for the twist test on X1 carbon. And this is the finishing on the P1P. The last 4 vertically printed test objects. They are almost finishing at the same time. Great. This is second group of the test objects and these will be annealed. And this group will be for the comparison between the colors, and those 2 vertically printed test objects for the layer adhesion are printed with 2 walls and 20% gyroid infill. I'm still not finished with these 2 materials, because I want to check somehow the print quality too, but not with the benchy. I have some better objects for this. An interesting thing I noticed, with smaller cross sections the X1 carbon is faster, because it has the aux fan compared to the P1P. They started in the same time. Interesting, the X1 carbon finished 15 minutes faster than the P1P, but I'm using the same filament profile. It's time to switch the color, and this version is also glass fiber, which goes to the X1 carbon. Teal color, and also it goes to the P1P, and I will use the same G-code. Each printing is okay so far, but I have to speed up this part. Well, this scientist will be finished during the night. It's time to move to the gray color. I'm not even supervising these printings anymore. The printability is like with the regular PLA. And the last spool for the printing, HT-PLA in black color. And finally all test objects are printed. Just very quickly to check the print quality, and here this is the regular HT-PLA. For the touch it is smoother compared to the glass fiber version, but the quality looks very equal. I believe that there are some overhangs which could came out better with the glass fiber version, but in this case really I cannot see any difference. Maybe just a slightly more stringing on the glass fiber version there between the legs. Gray and teal color, again very similar. Maybe one more string I can see on this one. And again the HT-PLA regular is on the left side, and just for the touch I can see some difference, but the colors are very similar, and the print quality too. The dryer is preheated. This is Sunlu E2, and I have to follow the temperature because I don't trust to the sensor which is here, because this is a prototype and I have to insert these test objects. Objects will cool down together with the dryer. Let's see what we have here. For the first look, they are okay. Just quickly to check the shrinking, and the design length is 80 mm, and I will measure above the elephant foot. This is HT-PLA. This is glass fiber version. HT-PLA annealed, quite noticeable shrinking, bigger than average ABS. And this is the glass fiber version, and here the shrinking is very similar to the regular ABS. And only on annealed HT-PLA I noticed some very minimal warping. Others are straight. The tensile test with horizontally printed objects. These are 4x4 mm in cross-section area. This is the glass fiber version. And noticeably stronger, but let's go back to the regular. On the left side you can follow the average values, but later I will analyze them again. This is the teal color, black color, and now glass fiber version of black color, and again noticeably stronger. And let's see if annealing helps. This is the regular HT-PLA, weaker, but let's see the glass fiber version, and also weaker. So from these test objects I have 4 because 2 are printed in that color comparison group and 2 are printed in that main group, and we can see that a regular HT-PLA has very similar strength in all 4 cases. Here we can see some small peak but nothing significant, and we can see that the glass fiber version is stronger, and annealing don't really help, actually it reduces the tensile strength. Layer adhesion test with vertical test objects. These are those with 4x4 mm cross-section area solid inside. And now let's see the annealed versions. A little bit weaker. And the glass fiber version, weaker too, and I will explain this later. And for the color comparison, I have 3 of these. 10x10 mm is the cross-section area, printed with 2 walls and 20% jarred infill. First for regular HT-PLA, gray color, teal, black, and now glass fiber versions, white, and glass fiber black. On the first layer adhesion test, 4x4 mm solid inside, we can see that the HT-PLA and the glass fiber version has acceptable layer adhesion, but unfortunately after the annealing it was weak. Probably the reason for the weaker layer adhesion after annealing is that micro warping, which will result some delamination or maybe even add some bending if the object itself is warped during this test. With this 10x10 with 2 watts and 20% jarred infill, we can see more or less similar values. Here we can see some smaller peak, but what I'm happy about is that the glass fiber version is not weaker compared to the regular HT-PLA. Shear test with horizontally printed objects, and usually glass fibers helps here, and now vertically printed, and in this position usually glass fibers reduce the strength. Exactly as expected, but the difference is not big. And actually in all 4 cases, these are good values. Torque or twist test, and I'm starting with horizontal printed versions. I record here the load at 90° rotation.
1.2.
And the maximum load.
0.7. 1.2.
Vertically printed usually breaks suddenly.
1.2.
And glass fiber version stronger in both cases. Impact test with this half kilogram hammer. This is HT-PLA. Zero position, glass fiber version. Interesting breaks, but actually this was broken when the hammer swing back. Let's analyze the footage. This is the zero position of the hammer, and this is the edge position after breaking HT-PLA, and this is after breaking the glass fiber version. This is not really typical that the glass fiber version is tougher compared to the non-reinforced version. And now impact test, and for the color comparison I have this thicker object 6 mm instead of 4, and I will use this stronger machine for this. On this machine I can measure the angle, but later I will convert this to the breaking energy in joules. Teal, black, white glass fiber, black glass fiber, The colors more or less similar toughness, except one peak in the gray color, and I know as a researcher that I should reprint and check this, but I don't have time for this because I am late with the video. But what is quite obvious that the glass fiber is tougher compared to the non-reinforced versions, which is not really a common case. 3-point bending test. Distance between supports is 50 mm, and these loads will be placed one by one, and I will measure the deformation after 1, 30 and 60 seconds. This is a deformation under 2.5 kilograms, under 5, later I will analyze the graph, and deformation under 10 kilograms. Smaller values are better. This is not bad, but we can see that the glass fiber versions are better compared to the non-reinforced versions, and also we can see that annealing helped in both cases. Bending test for the color comparison. Distance between supports is 64 mm, and I will place this 5 kg load and I will measure the deformation after exactly 30 seconds. Regular white. This part is speeded up. After 30 seconds, deformation of the white. Gray. On the left side you can follow the values. Teal. Black. And now glass fiber versions, less deformation, and this is the black glass fiber version. HT-PLA, very similar deformation between the colors, and the glass fiber version again very similar between the colors and less deformation compared to the non-reinforced version, which is typical for these materials. Creep test the deformation under the constant load. $15.49. 1491, 1386, 12.98. They will be measured every day, but in the video let's jump in the time. This is the last day of the measuring, and soon I will show you the numbers, but in both cases I can see that the glass fiber version is stronger than the regular, and also in both cases I can see that annealing helped compared to the non-annealed versions. Removing of the load. It's quite obvious that the glass fiber helps against the creeping, but also the annealing too. But let's see the numbers. On this graph we can see the deformation, the distance between two reference surfaces. And we can see more deformation on the HT-PLA compared to the glass fiber version, but we can also see that annealing helped. But this test is not about the bending, but about the creeping. And the difference between 2 days we can see on this graph, that's the creeping, and we can see only HT-PLA had some creeping even on the 5th day, and this is very typical for average PLA materials. All three are very good in this test, and basically they stop with the deformation after day 2. This is very minimal. Temperature test in the oven, and I need this for my documentation too. So 4 on the left side are regular HT-PLA, then glass fiber versions, and these two are annealed, a regular and glass fiber version. This is a time-lapse video, and don't be confused with the temperature dilatation of the sheet below these test objects. First deformation I noticed on the regular HT-PLA, then on the glass fiber versions, and then on annealed, regular and glass fiber version. But in every case that deformation started, but then it looks like it stopped for some time. That's why I stopped the experiment only at 183 degrees Celsius. And I removed this nut, which was the small load, and I just checked how hard they are, but in all 9 cases they became quite flexible on this temperature. One more temperature test. I want to see if I can reproduce that experiment from this picture. These two on the right side are the HT-PLA, and they are partly annealed. This means when I finish the printing I just raise the bed temperature to 90 degrees Celsius, and when it reached that temperature I immediately turned it off. Of course this method can be used only with the thinner objects like these ones. Pity I didn't include here a polycarbonate after the ASA, and this is a time-lapse video, but there are no jumps, so you can see how much time passed after that ASA deformed. All results one more time without any additional comments. Tensile test results, layer adhesion 2 types, shear test horizontally and vertically printed objects, bending deformations after 30 seconds, and this is more important, deformations after 1, 30 and 60 seconds. Bending test for the color comparison, torque or twist test, impact test, and this is impact test for the color comparison with thicker objects, and the temperature test. This was huge work, but not because the Polymaker is the channel sponsor, but because I think this is really big innovation. Maybe not the most heat-resistant material on the market, but one of the most heat-resistant which can be printed on open printers too, on Bamble Bay 1 Plus and Mark 4 and similar. And now those users can print something which can be inside the car and they will not deform on hot summer day. Or maybe if one of colors will get FDA certificate, I'm not sure what the other additives they use, but that would be great because we can use it in the food applications and it can be clean with the boiling. I already tested this. Now it still creeps like regular PLA, the HT-PLA. The annealing helps here, but I don't really like that shrinking and warping during this annealing. So that's why I really like the glass fiber version. And it's even tougher as it's better to the bending, so really great material. I hope all this doesn't sound like a marketing material, but that's why I'll try to show you all my measurings in the video too. But anyway, probably other reviewers will test this material soon. Anyway, this is my experience with HT-PLA and the GF version. And if you will have some other experience, write me down in the comment section. Thank you for watching and happy printing.